UCSD ECE 111 Lecture 2 Set 2, we will go through some important module elements in System Verilog and how we could use them in programming in this set. We so far just learned about the the assign. Now there is another block that is super useful in System Verilog, and that are the initial and always block. Initial and always have inherently a notion of a sequence in them, meaning that there should be something happening for them to do the next thing. And if you remember from your logic design course where we have the state machines, or we had states that are dependent on each other, this was pretty useful in that for those cases. The initial block is something that is only used in simulation and not really synthesizable into a piece of hardware, but it's very useful in writing test benches, which we will be discussing later in the class. The always block is also continuously executed as long as its sensitivity list is satisfied, meaning that there is something that needs to occur before the things inside the always block are run. And this sensitivity may be like what you have seen before in sequential design and finite state machine, may be sensitivity to a clock, or in a program you may assign sensitivity to the inputs that are coming to one block. If you're putting sensitivity to say A or B, this may not be the whole list of the inputs coming into your design. You could have other inputs. If you have always and then parenthesis star, it will be actually sensitive to anything that comes in and changes at the time. And then, there are two other constructs that are pretty useful in defining blocks of logic within the modules, and those are the begin and end, which are equivalent to curly braces in C. So the sensitivity list and begin and end is just making sure that block inside those curly brace-like constructs, which are begin and end here, are satisfied. In this case, we just have a simple XOR, which doesn't really need the begin and end, but we just put that for demonstration purposes. So if you remember from the previous lecture, assign statement is always also executed. So if you're writing combinational logic, for example, output is just the XOR of A and B, we could write it with assign like we've shown in the previous set, but we could also write it as always star sensitivity, which makes sure that anything changes in the input, it continually changes the output. The Verilog has different options for variable. You could define variable as a wire, and when you define a wire, what it means is that you're connecting components together, and all the variables, including the I/O ports, are by default wires. There is also the option of defining variables as registers, which saves a value as a part of a behavioral description language. But when we say a register, this doesn't necessarily translate into a register necessarily when we make a physical implementation or even a netlist implementation. Because remember, the software is optimizing things before it maps things to a netlist or to a physical design. But every time in a behavioral description we need to save a value, we define it as a register. Usually we use wires outside the initial always block, and registers are used inside the always block. And if we go back to the previous example, you see it here. So here the output is registered because we are inside the always block in this particular case, and here the output is just a wire because we are just having a combinational part that is a piece of wire. The signal values as Verilog gives us the capability, or system Verilog, which is an enhancement of the Verilog, is we could have logic as 0 or 1, but it also gives us the capability of define high impedance values. This is particularly useful if you're designing systems that are connected to buses that are running, that are deriving multiple things, and not everything is active all the time or connected to the bus all the time. And in the behavioral description, there is another very useful value that we can define, and that's a don't care. So X value is only something that we define in the behavioral description, but this is not going to be translated to a physical value. In reality, every time we say a X, we say we don't care what it will be in real life, and once the synthesis is done and a piece of hardware is generated, it's going to translate it to a 0 or 1 itself. There is no value called X in the physical world. The variables could be defined as bits or vectors of bits. Here, we see a wire which is, has 4 bits on it. Or we could concatenate these bits and vectors into larger vectors, like shown here. You could say for a sub 3, which means that the third value on array A is going to repeat it 4 times, and then we're going to repeat it, and then this is assigned to a 8-bit wire here. At your spare time, feel free to look at the slide, which defines the various operators for Verilog, which are used in arithmetic, logic, and relational operations. These are pretty standard in programming languages. I expect that you have seen them before. Please make sure that you review them, because when you write the language, you're going to use these constructs and operators. Here is just some examples if you're really writing pieces of code that are implementing this to go through. We will go through some of these operators in more details in further lectures. We could write Boolean logic here. A is X or Y and Z naught, or you could write it as a number. You could actually give to a wire a number value. Here, for B01, don't care means that we're going to define, a 4-bit value assigned to the 4 bits. Or to the 16-bit, you could assign a hex value like you've seen here. There is one more construct that is pretty useful in simulation, and we will see that on and on in the class, and that is a hash number, which you could put right after a sign. What this one does is it basically executes or assigns outputs from a combination of the input. Output is computed, for example, in simulation purposes, but then it shows that in simulation 3 clock signals later. And this doesn't have a unit. The unit is basically unit of a clock signal. This is pretty useful in simulation. The hash 3 doesn't mean anything in the physical implementation. It is not at all used. It's going to be ignored if you give that piece of code for actual physical implementation. But this is useful in simulation because it will help us simulate timing as we design our circuits. The next set is going to be describing module instantiation with some further examples for that.